All right, well, in 12 minutes, we're not going to do much. But, all right, so I'm going to flip these fast. Why? Because we only got 12 minutes. And if any time you don't get something, then you holler, right? All right, so this is the math that you're going to need to know. So we will cover it as we need it, right? Time complexity, right? The key here is that the time is a function, and we are going to cover in 3101, right? Time is a function from the size of the input. What's the size of the input? The number of bits to write the input down, to the running time, right? And what's running time? It could be the number of iterations. It could be the number of seconds. It could be the number of, right? And we do big O so that all of those are within a constant of each other, multiplicative constant, right? Right, so it's a mapping from size to the running time, right? Here we go, right? This is my father and this is me. My father defined exponential versus poly time, right? And so here's some time classes, right? You have to know what does it mean to be constant time. What does it mean to be log time, right? So constant time is what we were doing with stack, right? It doesn't matter how long the stack is, my time for pushing is fixed, is bounded by, right? Here we're saying for every, there exists a constant, a million, such that for every input, the running time is bounded by a million, right? Log search is binary time. Linear search, you have to look at the whole input, right? Binary search, you're not looking at the whole input, right? N log n is the time for sorting. Quadratic time is the time for slow sorting, right? Poly time, right? So here we're saying there exists the constant C, so that no matter how big your input is, the running time is bounded by the size of the input raised to the power of C, right? Exponential time is considered to be too ugly. You brute force. You try every possibility. Computable is any time, and then the halting problem, right? People good? And then you should know sort of the relative speeds of these, right? And here's some concrete examples. Here's another joke about my father, right? Humans are this big. My father's a little bigger. But it's not really completely true anymore because my brother is now, and my nephews are all bigger and even bigger. All right, so then here we can kind of say the relation, if this is what the time is for n, then what's the time for n plus 1, right? And you can sort of try to fill in this table to see how running time changes. If you want me to do this again slower, holler. Should I do this slower? You could, right? It's just saying, right? If n squared is the running time on n, if t is the running time on n squared, then in the running time on n plus 1, it's basically we're doing a little calculus, right? We got what's the effect of increasing it by 1. Exponential time, right? You should this is all covered in our class anyway. Let's see if we can leap forward to see what's not covered in this class. The log scale. Here's the example, right? Here's constant time, right? That pushing onto the stack is independent of the running of the size of the input, right? This says there exists the Java program, right? So and when I do first order logic, I played it as a game, right? When there exists, I have to come up with a Java program, right? So there's one Java program I come up with. And then I come up with one integer k, right? And then the adversary, knowing my k and knowing my program, gets to choose an input. And what has to be true about the input is that if I run this Java program on this input, the running time is bounded by my k, right? That's big O of 1. People know that? Binary search, we're going to cover, right? The running time is log n, right? Because if you don't know what log n is, you should notice if you start with n, and you divide it by 2, and divide it by 2, you divide it by 2, how many times do I divide it by 2 is log n until you get to 1, right? It's also, what is 2 to the log n base 2 equal? It equals n, right? Log n is the number I have to raise 2 to get n. So you definitely need to know that. Here, quadratic time is, right, here's time. We're going to cover this in class, but the time is n squared, because to insert a number takes n, and we have to do it n times, right? And here's an example where I think we do in class. This is a good example. It was on the 2011 exam, right? Here's an AND or NOT circuit, right? Here's an assignment to it. The assignment percolates down. Everybody know how this works? And so here's two questions. The one question is, if I give you a circuit and an assignment, right, how long does it take to compute the output? Right? So this was on the 2011 exam. Half the people didn't get it. Right? So what's the running time? Is, well, you got to look at each gate. Right? Each gate. So the running time is going to at least be proportional to the number of inputs, number of bits, and the number of gates. Right? Everybody good with that? Yeah? No? Yeah? All right, so here, now a different question is satisfiability. Right? The input is a circuit, and we don't get an assignment as input. The question is, does there exist a circuit, does there exist an assignment which will make it true? And there, the best algorithm we know about is to try all assignments. Right? And the number of assignments is 2 to the n. Right? Adding, right? We could say, what's here's the adding algorithm is linear, right? Because, yeah, you go through it in each one, right? But the quadratic algorithm is n squared, right? Because we take every number here and every number here and multiply them. Right? We're going to do this. This is actually also in our class. So this is also in our class we're going to do. We're going to say the kindergarten algorithm, well, maybe not kindergarten, the high school algorithm takes n squared time, right? And this is the kindergarten algorithm, a plus a plus a plus a b times, right? That takes order b time, right? So you can read this, or you can wait until we do it in class to find out which of these algorithms is faster. Right? Here's talking about different sizes of the input. We're going to do this in class. So all that, and here cryptography version we're going to do in class. Amortized time we're not going to do in class. So this is kind of a funny example, right? So what's the problem? Is you have an array that is getting, every iteration we make it one bigger. Right? And so if your arrays of this, it looks like this, then you can add something, you can add something, you can add something. Right? But at some point it gets full. Right? So here it's full. And what we're going to have to do then is throw this away and make it bigger in an array. Copy everything down. Right? So then we're asking, what's the amortized time for doing this? What does amortized time mean? It means if you were to do a total of n operations, then what is your total running time divided by n? Right? So if I add one extra, that takes me a constant time. I add one extra, it takes me a constant time. Right? But here, when it's full, I add one extra, it takes me a lot of time. Right? Does that make sense? So what's the amortized time? Here we're having a question. When I make it bigger, do I go from a list of size n to a list of size n plus c? Or do I go from a list of size n to doubling it? Right? People understand what we're doing here? Any questions? Right, so then, let's try these. Right, when you add, this is just saying, right, every time we add one, that doesn't cause any grief. Right, the grief comes in allocating the new memory. So let's say that to allocate an array of size k cost me k. Why? Because maybe I'm copying the things down. Or maybe it took me a while to allocate this memory. Right? So then I want to know, how does this incremental strategy work? Right? Well, first my array is of size c, then 2c, then 3c, then 4c, because that's how I roll. I make it c bigger every time, right? And eventually it gets to be of size n, and I stop. Right? People following that? Right? So then I can ask, well, what's the total time? Well, when I allocated this, it cost me c. When I allocated this, it cost me 2c. Right? So that's what it cost me, is the sum of those things. And what does this sum up to? Right? Well, we'll do summations, and it sums up to the number of steps squared. Right? There's a square in there. Right? So then if I ask for the time per iteration, right, it becomes order n time. Right? People kind of following that? No? Here, let c be just 5, then it's a constant. And so then this boils down to the sum of 1 plus 2 plus 3 plus 4 adds up to about n squared. Right? So the total time is about n squared. So, but I only did n operations. So the average time per operation is now n. Right? Which is bad. Right? Does that make sense? Right? So we come over to the other one. What happens if we double each time? Well, 1 plus 2 plus 4 plus 8 plus 16 sums up to the biggest guy, times 2 minus 1. Right? So then the sum is order the biggest guy, which is order n. And then if you look at what's the time per operation, right, then it's constant time. Right? Does that make sense? Everybody good? Have we run out of time? Okay, let's stop.